Welcome to the deep dive. Today we're going, well, really deep. Forget just scratching the surface. We're plunging right into the fabric of reality itself. We're questioning something so basic we barely think about it. Time. I mean, have you ever really stopped to ask what time is beyond, a clock ticking? What if our whole understanding, this idea of time just marching forward, has been kind of incomplete all along? So yeah, in this deep dive, we're exploring a truly groundbreaking new theory. It really challenges everything we thought we knew about time and space. Our main source today is this fascinating piece from the Debrief. It highlights the incredible work of Professor Gunther Kletschka at the University of Alaska Fairbanks. Definitely check it out if you want even more detail.
It's a really provocative idea. Conventional physics, Einstein's theories and all that, serves incredibly well. I mean, think GPS, understand the cosmos, amazing stuff. But there are still these huge mysteries left. Things that just don't quite add up. And maybe the biggest one, the sort of ultimate goal, is finding that theory of everything. The one single framework that can explain all the fundamental forces. It's been the dream for decades. And Kletschka's idea, this different way of looking at time, well, it might just offer some genuinely new paths towards solving those big puzzles. Audacious, definitely, but potentially revolutionary.
Okay, right. Let's try and unpack this a bit because for over a century now, our picture of the universe has been built on Einstein's spacetime, which has been, incredibly successful, right? It says we live in a universe with three dimensions of space, like length, width, height, your basic X, Y, Z axis, and then there's this single dimension of time, just one, moving in one direction. People call it the arrow of time. Always forward, past to future, no going back. And this model, it explains so much. Planetary orbits, light bending, the universe expanding. It's been the foundation.
Absolutely. It's the bedrock, like you said. But what's fascinating, and kind of frustrating for physicists, is that even with all its power, this standard model hasn't managed to deliver that unified theory of everything. See, you've got general relativity over here, brilliant for gravity, stars, galaxies, the big stuff. And then you've got quantum mechanics over there, flawless for describing atoms, particles, that tiny stuff. But try to put them together, especially in extreme situations like, say, inside a black hole or right at the Big Bang. They just clash. The math breaks down. You get nonsense answers like infinities. It's like having these two perfect maps of different regions that just won't line up at the border. There's a huge gap.
Right, that disconnect. And that's exactly where Professor Kletschka comes in with this, really bold proposal, a three-dimensional time theory. He's basically saying, hold on, maybe the fundamental structure of reality isn't what we thought. Oh, instead of the usual 4 dimensions, 3 space, one time his idea involves 6 combined dimensions of time and space. Now, okay, the idea of extra time dimensions isn't totally new in physics. People have played with it mathematically before. But here's the kicker, and this is really important. Kletschka says his theory isn't just math. He insists it's testable and verifiable. He's talking concrete experimental connections, multiple independent verification channels. This isn't just some abstract idea. He thinks we can actually prove it.
Exactly. And that testable and verifiable part, that's what makes scientists sit up and pay attention. In physics, you can have the most beautiful, elegant theory in the world. But if you can't test it, if it doesn't make predictions we can check with experiments or observations, it kind of stays philosophical. So Kletschka claiming his theory can be tested means he thinks there's a way to find actual evidence for it. It moves it from interesting thought to potential science. It's a big claim.
Okay, so here's where it gets really tricky to visualize maybe. But the article gives this great analogy to help us wrap our heads around 3-dimensional time. So forget just one path forward. Imagine this instead. Dimension 1 is pretty much what we already know. Picture yourself walking down a straight path, just moving forward. That's like our normal experience of time, yesterday, today, tomorrow, the familiar arrow.
Our standard linear progression. Got it.
Right. Now imagine a second path that crosses the first one, but it goes sideways. Now, if you could somehow step onto the sideways path, Kletschka suggests, and I'm quoting here, you might find that things could be slightly different, perhaps a different version of the same day. The key thing is, you're not moving forward or backward along your original timeline. You're exploring different possibilities of the same moment, sideways.
So it's like exploring the what-ifs of right now, not traveling to yesterday or tomorrow, like branching possibilities existing simultaneously.
Kind of, yeah. Like different potential outcomes or variations of the same event accessible through this second time dimension. And then building on that, there's the third dimension of time. This third one represents the transition between these different potential outcomes. So you've got forward motion, sideways exploration of possibilities, and then this third dimension allowing movement between those possibilities. It suggests reality is much more fluid than we think.
Wow. Okay, so if we tie this back to the bigger picture, Klotechka says something really profound about this. He says, these three time dimensions are the primary fabric of everything, like the canvas of a painting. That's a direct quote. Think of that. He's not just adding dimensions. He's saying time in this three-dimensional form is the fundamental background, the absolute foundation. And space, he says space with its three dimensions still exists, but it's more like the paint on the canvas rather than the canvas itself. So time is the canvas, space is the picture painted on it. That completely flips the usual way we think about their relationship.
Oh, okay. That is a fundamental reorientation. It's almost like space emerges from time or exists on time rather than alongside it as an equal partner. So just to make sure we're getting this, and for everyone listening, it's not just 6 dimensions thrown together. It's these 3 time dimensions making the base reality the canvas. And our familiar 3 space dimensions are like painted on top or exist within that temporal canvas. Is that the idea?
That seems to be the core concept, yes. A nested reality, as you put it. Time is the fundamental substrate. Space is a property or feature manifesting within or upon that substrate. And the immediate implication, well, it means our standard view, where time is just this single line moving forward, is drastically incomplete. If time really is multidimensional and primary, it opens up totally new ways to think about, well, everything. Causality, existence itself, maybe even how different realities could branch off, not just theoretically, but as part of the actual geometry of the universe. It paints a picture of a cosmos that's way more interconnected, maybe even more malleable than we ever imagined.
Okay, so it's a mind-bending idea for sure, but what does it actually do for physics? Why is this potentially more than just a cool abstract concept? You mentioned it holds some grand promises, right? Especially for bridging that gap between quantum mechanics and gravity. That's the big one, isn't it? The holy grail.
Absolutely, that's the holy grail. For nearly 100 years, physicists have been stuck on this problem. Quantum mechanics rules the small scale, general relativity rules the large scale, and they just don't speak the same language. They give contradictory results when you try to use them together in really extreme scenarios, like the Big Bang or black holes. We desperately need a theory of quantum gravity to unite them. And this is where Klotechka's theory comes in with a potential solution. One big advantage, he claims, is that his model avoids a trap some earlier multi-time dimension ideas fell into. That trap is messing up cause and effect. If you're not careful with extra time dimensions, the math can accidentally allow effects to happen before their causes, which is, well, it's not how our universe seems to work. But Klotechka argues his theory maintains causality. Causes still come before effects. It's just embedded within a, quote, more complex mathematical structure.
Okay, that's crucial. So it's not like suddenly anything goes, paradoxes everywhere. How does it keep cause and effect lined up if you've got these extra sideways time paths?
That's a really important point. He's designed the mathematical framework specifically to avoid those paradoxes. It's not about jumping around randomly in time. Think of it less like chaotic time travel and more like, maybe a complex river system. There are multiple channels and currents, the extra time dimensions, but the water, causality, still fundamentally flows downstream from cause to effect. The structure, though more intricate, apparently preserves that essential ordering. It allows for richness and variation without breaking the fundamental rules of logic we observe.
That makes more sense. Okay. And the most exciting promise, the really tantalizing part, is bridging that quantum gravity divide, getting us to that unified theory of everything. If this works, it would finally unite the 4 fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, into a single elegant description of reality. That's the ultimate goal. And Klotechka isn't just saying, maybe it could. The article mentions he provides specific evidence. It says his theory successfully reproduces the known masses of particles, such as electrons, muons, and quarks, and explains why these particles have these masses. That sounds huge. If it can actually predict those fundamental values, why is getting those masses right such a big deal for a theory like this?
Oh, it's a massive deal. Pun slightly intended, maybe. But seriously, in theoretical physics, lots of models can explain things conceptually, but they often need you to plug in known values or fiddle with parameters to make them fit the experimental data. If Klotechka's theory can derive these fundamental particle masses, the electron's mass, the muon's mass, quark masses, directly from his core principles, without needing to tweak things afterwards, that's incredibly powerful. It means the theory isn't just describing what we see, it's potentially explaining it at a deeper level. It gives it concrete, testable predictions anchored in real-world measurements. That kind of quantitative success is what separates a promising idea from a truly compelling one. And it naturally leads to the question, okay, if this is real, where would we see its effects most clearly? Some physicists, like Itzhak Bars, who's mentioned in the debrief article, think the effects of this kind of multidimensional time structure might really show up in incredibly high-energy situations. Think the very early universe, moments after the Big Bang. Back then, energies were so extreme that maybe these extra time dimensions were more apparent or influential. If the theory holds up under those conditions, it can answer fundamental questions that have baffled scientists for ages. Questions about how the universe started, why it has the properties it does, maybe even shed light on things like dark matter or dark energy. Like Kletetschka himself says, unifying physics might mean we have to fundamentally rethink reality itself. It's about adopting a completely new perspective.
It's definitely an ambitious, really compelling vision. But, with any big new idea that challenges the status quo, there must be hurdles, right? Are there parts of this theory that are still really difficult? Maybe areas where the math gets super complex, or where the predictions need more refinement to perfectly match all observations.
That's absolutely fair to ask. And yes, any theory this revolutionary is still, in the early days in terms of widespread acceptance and testing. The debrief article highlights its potential, but the broader scientific community will be digging into the math, looking for more testable predictions, especially ones we can check with experiments we could actually build now or soon. Making sure it's consistent with everything we already know about physics is a huge task. The very idea of rethinking time is so radical it's going to face intense scrutiny. But honestly, that's good. That's how science works. The big challenge now is figuring out how to design experiments that can effectively probe these extra dimensions of time, if they exist. That's the next frontier for this idea.
Wow. Okay, what a truly mind-bending deep dive this has been. We've gone from our simple ticking clock to this idea that time might be this intricate, multidimensional canvas underlying, well, everything. It really is like realizing the movie screen isn't flat, but this huge interactive landscape with hidden depths. If you enjoyed exploring this with us, let us know in the comments. And hey, hitting that like or subscribe button helps others find these discussions too.
And the takeaway here really is the potential significance. As Professor Kletetschka stresses, this isn't meant to be just a mathematical game. It's proposed as a testable, verifiable concept that could genuinely reshape our understanding of the cosmos. And maybe, just maybe, give us the key to unifying physics. It's the kind of thinking that could rewrite the textbooks.
Absolutely. So it leaves you wondering, doesn't it? If time does have these extra dimensions, these sideways paths and transitions between possibilities, what does that imply for how we understand cause and effect, or even for those sci-fi ideas about alternate realities? Could they be, in some way, just a sideways step in time? It just shows how many deep mysteries might still be hiding right under our noses, just waiting for us to find a new way to look. A lot to think about there.